On the 26th of August, 2025, a radar dish found nothing. It was aimed at a 380-metre rock passing near Earth. 5 days later, another telescope found it far outside every prediction we had made. The gap was 19 standard deviations, which means the equation itself was simply wrong. Something had been pushing that rock for 27 years without anyone noticing it. So one question drives everything that follows, and nobody can answer it yet. Was that object the rare exception, or the first one we happened to catch? Subscribe now, and tell me in the comments where you are watching from tonight. Let us get into what that missing rock actually means for Earth. Part 1. The night the antenna found nothing. The Goldstone complex sits in the Mojave Desert, about 2 hours north of Los Angeles. Its largest dish measures 70 meters across and weighs roughly 3,000 tons. That antenna is one of the few instruments on Earth capable of ranging asteroids. It transmits a radio pulse, waits, and catches the faint echo that returns. Radar gives you something optical telescopes cannot easily provide, which is distance. A camera tells you the direction an object sits in, and it does that beautifully. It struggles to tell you how far away that object actually is. Radar measures the round-trip time of the pulse and converts it into range. For a body a few million kilometres out, that measurement is accurate to within meters. There is one weakness in that method, and it explains this entire story. A radar dish has to be told exactly where to point before it listens. The beam of the Goldstone antenna covers about 70 arcseconds of sky. The full moon, for comparison, spans roughly 1,800 arcseconds across, so that beam is about 1/25th the width of the moon. Optical astronomers face no such constraint when they hunt for something. A wide-field camera photographs a large patch and finds whatever happens to be inside. Radar demands that you already know the answer before you ask the question. It is a needle rather than a floodlight, aimed at one exact spot. You cannot sweep it around hunting for something that has wandered. Instead, you compute a prediction, you aim at the prediction, and you wait for the echo. Predictions like that are not produced by a single person at a desk. They come from software maintained over decades, cross-checked between institutions on different continents. The same numerical machinery guides spacecraft and computes impact probabilities for every catalogued object. The prediction for that night came from an unusually solid orbit. The object had been discovered on the 17th of September, 1998. It was last photographed on the 27th of October, 2016. Between those dates, astronomers had logged 148 separate position measurements. Hold that number, because it is larger than most people assume. 148 measurements across 18 years is a good observational arc. By the standards of near-Earth object tracking, that orbit was considered well determined. Nobody involved expected the slightest difficulty in finding that object again. The object also carried a specific label in the catalogue. It was flagged as potentially hazardous, which is a technical designation rather than a warning. That flag means an object is large enough and passes close enough to warrant monitoring. Roughly 2,500 known objects currently carry that same flag. This was one of them, and it had carried it for decades. That potentially hazardous label is not applied by anyone's judgment. It comes from two hard numerical thresholds applied automatically to every orbit. The object must measure larger than roughly 140 meters across. Its orbit must also pass within about 7.5 million kilometers of ours. Cross both thresholds and the label attaches itself, regardless of any actual impact probability. The Goldstone antenna belongs to the Deep Space Network, which normally talks to spacecraft. It tracks missions across the solar system and receives their data streams. Asteroid radar is a secondary use of that hardware, squeezed between mission obligations. only a handful of facilities anywhere on Earth can perform the task. After 2016, the rock simply vanished from every observing list. Its orbit carries it out to about 4.7 times the Earth-Sun distance. A full circuit takes roughly 4.5 years to complete. Out at that distance, it becomes far too faint for routine observation. So it sat in the database, orbit computed, risk assessed, and effectively forgotten. It is worth remembering what asteroid searching looked like in 1998. A handful of programs were grinding through the sky with modest telescopes. Digital detectors had only recently replaced photographic plates for this kind of work. A discovery then meant a few nights of positions and a provisional designation. Follow-up depended on somebody caring enough to point a telescope again later. Thousands of objects were found in that era and never adequately tracked afterward. Our object was luckier than most, and it still ended up in this situation. It came back around in the summer of 2025. Its closest approach to the Sun came on the 21st of July that year. Its closest approach to Earth followed at the end of August. The missed distance was about 0.02 astronomical units, near 3 million kilometres. That is roughly 8 times the distance between Earth and the Moon. For radar, that is a genuine opportunity, and those opportunities are rationed carefully. Time on the Goldstone antenna is contested by missions across the entire solar system. Pay close attention to how rare that particular opportunity actually was. Radar can only reach an object during a narrow window near closest approach. For this body, that window opens roughly once every 4.5 years. Most of those windows fall at geometries that make observation impossible anyway. Somebody made the case for this rock, and the case was approved. The observation was scheduled for the 26th of August. The dish pointed exactly where 2.5 centuries of orbital mechanics said it would be. The transmitter fired, and the receiver listened through the expected round-trip window. Nothing came back through that window, and the operators logged an empty result. Now, a failed radar detection is not automatically interesting, and I want to be honest about that. The standard explanations are dull, and they are usually correct. Perhaps the object is smaller than the infrared estimate suggested, weakening the echo. Perhaps its surface is unusually radar dark and absorbs more than it reflects. Perhaps there was an equipment fault, or a scheduling error, or simple bad luck. Failures like that happen several times a year and almost never produce a paper. They get written into a log, and the observing time moves to the next target. What made this particular failure different was what a small observatory in Brazil found 5 days later. That detection turned an ordinary bad night into the most consequential planetary defense measurement of the year. Part 2. 153 seconds of missing sky. It is worth appreciating who actually recovered this object in the end. It was not one of the great national facilities with enormous budgets. It was a small observatory doing patient, unglamorous, essential work. Much of near-Earth object follow-up happens exactly that way. Large surveys find things, and smaller observatories keep track of them afterward. The recovery came from an observatory called Sunir in the hills of Serra da Piedade. Its name stands for the Southern Observatory for Near-Earth Asteroids Research. It is a modest facility by professional standards, run with real dedication and limited resources. On the 31st of August 2025, it photographed the missing object. Orbit determination works by a method called least squares fitting. You start with a trial orbit and calculate where it predicts each observation should fall. You compare those predictions against what the telescopes actually recorded. The differences between them are called residuals, and you adjust until the residuals shrink. When the residuals scatter randomly and stay small, your orbit is correct. When they show a systematic pattern instead, something in your model is wrong. That pattern is the signature every orbit analyst is trained to notice. Then somebody compared the measured position against the prediction that Goldstone had used. The two positions did not match, and the size of the gap mattered. The gap between them was 153 arcseconds. Convert that angle into actual distance, and the scale becomes clearer. At a range of 3 million kilometres, 153 arcseconds is enormous. The object was displaced by well over 2,000 kilometres from its predicted position. 2,000 kilometres is roughly the distance from London to Moscow. That is how far off the prediction was, after 18 years of careful measurement. I want to be precise about how strange that figure actually is. In absolute terms, 153 arcseconds is a small angle. It is roughly 1/12 the apparent width of the full moon in our sky. Standing outside on a clear night, you would never perceive a gap that size. But this was not a rough guess about where a rock might turn up. It was a prediction built from 18 years of measurements and extremely well-tested physics. Gravity is the best understood force in the whole of science. Feed the positions of the sun and planets into the equations and the answers work. Those equations landed spacecraft on Mars and threaded probes between the rings of Saturn. They predicted the return of Halley's comet and the position of Neptune before anyone saw it. They do not miss by 153 arcseconds. Every orbit fit also produces a formal uncertainty, which is the model reporting its own confidence. That uncertainty is calculated from the scatter in the underlying observations. For this object, with its long arc, that uncertainty was tight. Measured against it, the miss came to 19 standard deviations. Let me translate 19 sigma into language that carries its actual weight. In experimental physics, 5 sigma is the threshold for declaring a genuine discovery. 5 sigma means the odds of a statistical fluke are vanishingly small. They sit somewhere near 1 chance in 3.5 million. That is the standard the Higgs boson had to clear before anyone announced it. This particular result came in at 19 standard deviations instead of 5. It helps to walk down that scale to understand where 19 sits. A 3 sigma result in most fields is interesting, but frequently wrong. A 5 sigma result is treated as established and gets published as discovery. Beyond about 8 sigma, statisticians stop quoting probabilities because they lose meaning. At that level, probability stops being a useful way to describe the situation. You are no longer looking at an unlucky measurement or a stretched error bar. You are looking at a model that does not describe the object it is modelling. A force was acting on that rock, and the equation did not contain it. And here is the detail that turns this from curious into serious. The better the orbit was, the worse this particular failure ended up looking. Read that line again, because it inverts the intuition most people bring here. A poorly observed object carries a large uncertainty around its predicted position. If such an object turns up somewhere unexpected, the miss looks minor. It registers as a modest 2 or 3 sigma event and nothing more. Astronomers shrug, add the new data, and refine the orbit. This particular object had been observed carefully across 18 separate years. Its uncertainty was small precisely because the data behind it was good, so the same physical displacement, measured against a tighter error bar, exploded into 19 sigma. The confidence in that orbit is exactly what made the failure visible. Without those 148 measurements, nobody would have noticed anything unusual at all. That sets up the question the research team faced next. A force was missing from the model, and the size of the discrepancy could reveal its strength. Working backwards from a deviation to its cause is one of the oldest methods in astronomy. Neptune itself was found that way back in 1846. Astronomers traced unexplained wobbles in the orbit of Uranus to a hidden planet. There is something quietly satisfying about how that fit behaved once corrected. Adding the extra acceleration term did not merely reduce the discrepancy slightly, it collapsed the residuals across the entire 27-year data set at once. Every observation from 1998 onward suddenly agreed with the model. That is the signature of a correct explanation rather than a convenient patch. A wrong term fixes one epoch and breaks another, and this one fixed everything. So they ran that calculation, and the resulting number was genuinely surprising. It ruled out almost every explanation the team had expected to find. Part 3. The number that ruled out every innocent explanation. A body pushed by something other than gravity feels that push in 3 directions. Astronomers separate those directions carefully because each one leaves a different signature. One component points directly away from the sun, driven by heat and light. A second runs along the direction of travel, which orbital mechanics calls the transverse component. A third pushes perpendicular to the orbital plane, lifting or dropping the object slightly. For this object, the transverse term was the one carrying almost all the signal. The team fitted every observation from 1998 through to the recovery data. Then, they solved for how large that transverse push would need to be. The answer came back at 1 point, 4 times 10 to the negative 11th. That figure is measured in meters per second squared, the standard unit of acceleration. The uncertainty on that figure was roughly 1 part in 14, which is a solid measurement. Numbers written in that exponential form can slide past without registering. 10 to the negative 11th means a decimal point followed by 10 zeros. Only then does the first meaningful digit appear in the figure. I want you to feel the weight of how small that acceleration actually is. The gravity holding you in your chair accelerates you at 9.8 meters per second squared. This push is about 100 billion times weaker than the pull of our planet. Picture a stalled car sitting on a perfectly flat road with the handbrake released. Now imagine pressing one finger against the rear bumper, gently, with no real effort. In the first second of that push, nothing visible happens at all. In the first minute, you would swear the car had not moved. That is roughly the scale of force we are discussing here, yet that same faint push threw a 380-meter body off course. It drifted far enough that our most precise instrument missed it completely. The difference is that space removes the part of the analogy that saves you. On a real road, friction and air resistance fight back and eventually cancel your push. In vacuum, there is nothing to cancel anything, so every push is permanent. That finger never lifts, the car never stops gaining speed, and nothing ever settles. Keep that image in your head because it explains the whole compounding problem later. It is worth noting which of the 3 directional components carried the signal. The radial term, pointing away from the sun, was not the informative one. The out-of-plane term was not the informative one either. The transverse component dominated, and that has a specific physical meaning. A push along the direction of travel changes the object's orbital energy directly. Radial pushes mostly change the shape of the orbit rather than its timing. So the team worked through the list of forces that could produce such a push. The first candidate was sunlight itself, since photons carry momentum and genuinely do shove things. That effect is real, it is measurable, and it is the principle behind solar sails. But radiation pressure on a body of this mass falls short by orders of magnitude. That candidate was ruled out quickly and without any serious argument. The second candidate demanded far more care because it is the standard explanation in this field. It is called the Yarkovsky effect, and I will explain its mechanics properly in a later part. The short version is that a spinning rock absorbs sunlight and re-radiates that heat slightly later. That delay produces a small thermal thrust, and it has been measured on hundreds of asteroids. So the researchers calculated the largest Yarkovsky acceleration this object could possibly experience. They did not use a likely value or a typical configuration for that calculation. They used the absolute physical ceiling, assuming the most favourable arrangement imaginable. That ceiling landed at about 1.3 times 10 to the negative 12th. Again, the units here are meters per second squared, matching the measured value. The measured value was 10 times larger than the ceiling. Let me say that again, because the entire investigation turns on this comparison. The observed push exceeded the strongest possible thermal push by a full factor of 10. No arrangement of spin, shape, or surface material could close a gap that wide. Before accepting that conclusion, the team also considered less exotic possibilities. Errors in the historical astrometry could in principle mimic a small acceleration. Poor observations from the 1990s might have dragged the fit astray. That explanation fails for a simple reason that is worth stating. Bad data produces scattered residuals rather than a smooth, consistent one-directional drift, which leaves exactly one mechanism that anybody has ever demonstrated in the solar system. The object must be throwing material overboard and receiving a kick in return. Ice somewhere on that body is turning straight into vapour and escaping into vacuum. By the plainest possible reading of Newton's third law, that makes the rock a rocket. It is a slow, weak, and almost completely silent rocket, but the physics is identical. The team calculated the production rate that such a thrust would demand. They arrived at roughly 1.2 times 10 to the 24th water molecules per second. That sounds enormous, and in raw molecule counts it certainly is. Molecules, however, are extraordinarily small, so the practical output remains a whisper. It is nowhere near enough to produce anything a survey telescope would notice. And that was precisely the problem facing the researchers in the autumn of 2025. An orbit fit alone cannot justify reclassifying an object tracked for 27 years. Reviewers would demand physical evidence, not a parameter added to a model. Somebody was going to have to photograph a tail that everyone had already failed to see. Part 4. Chasing a tail that 53 photographs had already missed. The first move in any search like this is to check whether the answer already exists. Before booking time on the largest telescopes on Earth, you search the archives. Somebody has usually photographed your target already without realizing what they had. The Atlas survey had done exactly that from its half-meter telescope on Haleakala in Hawaii. Its full name is the Asteroid Terrestrial Impact Last Alert System, and it hunts moving objects nightly. It had captured this particular rock across 53 separate images. In every one of those 53 frames, the object appeared as a simple point of light. There was no coma, no fuzz, and no hint of any tail whatsoever. It looked exactly like a small asteroid, which is what everyone had always called it. Count those images again, because that null result defines the entire problem. A survey built specifically to watch near-Earth objects had the target in frame repeatedly. It saw nothing unusual on any of those nights, and it was working perfectly. Had the orbit not betrayed the object, it would still be catalogued as an asteroid today. Every prediction we make about it would still rest on the wrong physics. There is a reason survey telescopes miss faint structure like this routinely. Their exposures are deliberately short, because they must cover enormous areas of sky nightly. A short exposure gathers few photons, and faint extended features need many photons. Depth and coverage pull against each other in every observing program ever designed. Survey instruments choose coverage, which is exactly the right choice for finding moving objects. So the team escalated the search to considerably larger telescopes. On the 13th and 14th of September, they turned to La Silla in Chile. There they used the Danish 1.54 meter telescope. They took a series of images through a red filter and stacked them together. Stacking is the standard technique for pulling faint structure out of background noise. You take many exposures and align them on the moving object rather than the stars. Then you add those aligned frames together so the random noise partially cancels while real signal accumulates. In the stacked frames, something faint appeared right beside the moving object. It was a tail, faint and narrow, sitting right at the edge of detectability. That result is suggestive, and it is a very long way from proof. Stacking artifacts are genuinely common, and background stars smear into trails when you track a moving target. Any experienced observer treats a marginal detection as a hypothesis, rather than a conclusion. So on the 17th and 18th of September, they moved to Mauna Kea in Hawaii. The Canada-France-Hawaii telescope carries 3.6 meters of aperture on an exceptional sight. The tail appeared again, this time reaching roughly 20 arc-seconds from the nucleus. Its surface brightness remained very low, meaning no single short exposure would ever reveal it. But two independent telescopes now agreed, which is the point at which people start believing. Then, on the 30th of September, they brought the question to Cerro Paranal in Chile. There they used one unit of the Very Large Telescope, carrying 8.2 meters of glass. They took 100 separate exposures, each running 60 seconds, on a single dark rock. That is roughly an hour and 40 minutes of accumulated photons on one faint moving target. Slow down on what that sequence represents in terms of effort. 3 separate observatories on 2 continents were coordinated across 17 days. Each one was chasing something that previous instruments had failed to record. In the combined image, the tail was unambiguous, narrow, and clearly composed of dust. Paranal sits on a mountain in the Atacama Desert of northern Chile. It is one of the driest places on the surface of this planet. That dryness is precisely why the observatory was built on that particular ridge. Water vapor in the atmosphere blurs and absorbs light before it reaches a mirror. Remove the water and faint objects become measurably easier to detect. Olivier Hainaut is an astronomer at the European Southern Observatory and a study co-author. He reported that the collected images showed a weak but clear tail. That tail confirmed the object really was a comet, rather than an asteroid. He framed the exercise as ordinary scientific method, rather than anything dramatic. You form a hypothesis, and then you go out and test it properly. That confirmation is the exact moment the official classification formally changed. The object now carries a second designation, with a P prefix in front of it. In small body astronomy, that prefix marks a confirmed periodic comet rather than an asteroid, and buried in that dust analysis sits the detail that explains 27 years of invisibility. The material had been released continuously across a 10-day window. That window ran from roughly the 29th of August to the 7th of September. More importantly, the grains in that tail measured around 400 microns across. 400 microns works out to 4/10 of a single millimeter. That size places those particles firmly in the coarse sand range. Think of the difference between a cloud of smoke and a handful of beach sand. Smoke hangs in the air and catches light from every direction, glowing brightly. Sand falls through the same beam of light and scatters almost nothing back at you. Both might contain the same total mass of material, yet only one of them is visible. A classical comet looks spectacular because its dust is fine, and fine dust scatters sunlight efficiently. Pack identical mass into grains 1,000 times larger, and the total scattering surface collapses. The comet then goes dark to almost every instrument pointed at it. The mass still leaves, the thrust still builds, and the underlying physics never changes at all. It simply stops looking like anything worth a second glance. Hold on to that sand and smoke comparison, because it returns when we count the suspects. This object was never hiding because it was inactive or unusual in any exotic way. It was hiding because its dust happened to be the wrong size to see, which raises a question with genuinely uncomfortable implications for the rest of the catalogue. If grain size decides visibility, then how many other rocks are venting quietly right now? Before that question can be answered honestly, something more basic has to be established first. The boundary this object supposedly crossed may never have been a real boundary at all. Part 5. The boundary that was never actually there. Ask most people to separate an asteroid from a comet and you get the schoolroom answer. Asteroids are rocks that live between Mars and Jupiter, and comets are dirty snowballs. Comets arrive from the outer darkness on long loops and grow spectacular tails near the Sun. That description is not wrong so much as dangerously incomplete. It describes the two extremes of a spectrum while pretending to describe a boundary. That distinction matters most for near-Earth objects, the only population planetary defense tracks. For that group, the boundary has been quietly dissolving for about 30 years. Here is the measurement professionals actually reach for when they need to classify something. It is called the Tisserand parameter with respect to Jupiter, and it comes from the orbit. It is a single number describing how strongly Jupiter dominates an object's dynamical history. Notice carefully what that particular number is not telling you. It is not a measurement of what the object is made from at all. It is a measurement of pedigree, of where the object has been and who controls it. Objects with a Tisserand value above 3 are dynamically classified as asteroids. Their orbits sit in territory that Jupiter cannot easily reshuffle over long timescales. Objects with a value between 2 and 3 fall into the Jupiter family comet regime. Those are bodies whose orbits Jupiter actively manages, and that population is historically fed from beyond Neptune. The object at the centre of this story has a Tisserand parameter of 2.9. Sit with that figure for a moment, because it was never hidden from anyone. It sat inside the comet range the entire time, in public data, for 27 years. Anybody with a browser could have looked it up on any afternoon they chose. That object is also very far from alone inside that range. As of late 2025, 2009 known near-Earth asteroids share it. 285 of those 2,000 carry the potentially hazardous designation. I want to be careful here, because overstating this would be genuinely misleading. A Tisserand value between 2 and 3 does not prove that an object is a comet. It means the orbit looks cometary, and gravitational shuffling can move real asteroids into that zone. Many of those 2,000 objects are almost certainly ordinary rock and nothing more. The parameter is a flag rather than a verdict, and it should be read that way. But in this one confirmed case, the flag was correct, and nobody was treating it as actionable. It helps to know where that Jupiter family population originally comes from. Most of those bodies begin far beyond Neptune, in a flattened disk of frozen material. Occasionally one gets nudged inward by a gravitational interaction out there. Neptune then hands it to Uranus, and Uranus eventually hands it to Jupiter. Jupiter captures it into a shorter orbit that reaches into the inner solar system. Every object arriving by that route carries ice, because it formed where ice survives. Now add the physical evidence, because the orbit was not the only quietly strange thing here. Radar tells you more than simply where an object sits in space. It reports on the texture of the surface that reflected your pulse. You transmit a circularly polarized radio wave and measure how the polarization comes back. Some energy returns with the polarization reversed, and some returns with the original sense preserved. The ratio between those two returns is called the circular polarization ratio. It measures roughly how rough and jumbled a surface is at centimetre scales. For near-Earth asteroids, that ratio clusters around 0.3 across the well-studied population. Eros comes in at 0.28 and Itokawa sits at 0.27. Tutatis measures 0.29, while Bennu returns 0.18. Didymos, the target of our first deflection experiment, gives 0.20. These are the rocks we have visited with spacecraft and characterized in genuine detail. They cluster tightly, which is exactly what you expect from a single physical population. Our object came in at 0.09 plus or minus 0.03. That value does not sit anywhere near the asteroid cluster on that scale. It sits in comet nucleus territory, well below everything we had visited. Its radar reflectivity told the same story, arriving at roughly 0.04. Then there is the albedo, meaning the fraction of sunlight the surface reflects back. Infrared measurements put that figure at about 0.058. Just under 6% of the light falling on that body ever leaves again. Set that figure beside something familiar in order to make it concrete. Fresh asphalt reflects around 4 to 12% of the light striking it. This object is roughly as dark as a newly laid road surface in summer. That darkness is exactly what a processed comet nucleus should look like after repeated solar passes. The volatile material near the surface bakes away and leaves a crust of carbon-rich residue. The body ends up coated in something closer to soot than to stone. Infrared measurement is how that diameter figure was obtained in the first place. An object in sunlight absorbs energy and re-emits it as heat. Measuring that heat tells you the surface area doing the emitting. Combine the heat measurement with the visible brightness, and both size and albedo follow. Its diameter measured 380 meters, with an uncertainty of 57 meters. Radar independently constrained that diameter to something under 600 meters across. That combination makes it the smallest comet ever observed by radar from Earth. So consider the complete picture as it stood before July of 2026. A very dark object sat in the catalogue with an orbit inside the comet range. Its radar signature matched comet nuclei rather than any asteroid we had ever visited. Its reflectivity matched comet nuclei as well, and it was flagged as potentially hazardous. Every property that object had was screaming comet, except for the single property we used to decide. It simply did not look anything like a comet through a telescope. And that gap is the real failure, sitting underneath the whole story. Our classification system has been resting on a visual test that anyone can apply. Does the object have a visible tail, and can a survey camera resolve it? Consider how that visual test came to exist in the first place. Nobody sat down and designed it as a classification scheme. It emerged from what early astronomers could actually see through their instruments. Comets were the ones with tails, because tails were the only distinguishing feature available. We inherited that distinction and built a modern catalogue on top of it. That test performs beautifully at the extremes of the population and fails silently in the middle. Unfortunately, the middle is precisely where the objects that concern planetary defence tend to live. Before the consequences of that failure make sense, one more thing needs establishing. This crack was visible long before anyone fell through it, and one object should have warned us. Part 6. The rock that feeds a meteor shower it has no right to feed. An object called Phaethon was discovered in 1983 by an infrared survey satellite. It measures roughly 5 kilometres across and is catalogued to this day as an asteroid. Its orbit brings it closer to the Sun than any other named body its size. At its closest approach, it comes within about 1/7 of Earth's distance from the Sun. Surface temperatures there climb to somewhere near 700 degrees Celsius. That is hot enough to make rock glow visibly in the dark. Here is the problem that Phaethon has posed for the last 40 years. It is the parent body of the Geminid meteor shower every December. Meteor showers happen when Earth ploughs through a stream of debris left along an orbit. Comets create those streams naturally, because comets shed material every time they approach the Sun. Asteroids are not supposed to create them, because asteroids are supposed to be inert. Track the other major showers, and the pattern holds without exception. The Perseids in August trace back to comet Swift-Tuttle, which is a genuine comet. The Orionids in October and the Eta Aquarids in May both come from Halley. The Geminids, one of the most reliable showers of the entire year, trace back to an asteroid. So that contradiction has been sitting in plain sight since the 1980s. An object classified as rock is behaving like ice, feeding a debris stream without a normal coma. The field even coined a phrase to describe it, calling Phaethon a rock comet. That phrase is worth pausing on, because of what it quietly admits. Inventing a hybrid term is how a discipline concedes that its two categories have stopped working. Do not lose that detail, because it recurs in every case that follows. A hybrid label is what a field produces when its categories fail. Closer observation made Phaethon considerably stranger rather than any simpler. Near its closest approach to the Sun, it brightens noticeably and produces a visible tail. Analysis suggested that tail is not built the way a normal comet tail is built. A conventional comet tail forms when escaping water vapour drags dust along with it. The evidence at Phaethon instead points towards sodium boiling directly off the scorching surface. The tail appears to be made largely of metal vapour rather than water and dust. That tells you something important about the range of options available here. There is more than one way for a small body to shed material into space. There is also more than one way to build a visible tail. Our visual test was only ever calibrated on the most common version. The Geminids themselves are worth a moment of closer attention. They peak each December and regularly produce over 100 meteors per hour. They are brighter and slower than most showers, which makes them popular with observers. That stream contains far more mass than Phaethon appears capable of shedding today. Something more violent probably happened to that object in the past. Now add the evidence that came from actually going to these objects. Between 2018 and 2021, 2 spacecraft operated at 2 near-Earth asteroids. The Japanese Hayabusa 2 mission worked at Ryugu, while OSIRIS-REx from NASA studied Bennu. Both targets are classic dark carbonaceous bodies of the sort that fill the near-Earth population. Both were widely expected to be dry rubble piles held together by feeble gravity, essentially loose gravel, carrying no volatile content that anyone thought worth discussing. What both missions found instead was hydrated minerals scattered through the surface material, clays, in other words, altered by liquid water at some point in these bodies' histories. The returned laboratory samples confirmed it, alongside a surprising abundance of organic compounds. At Bennu, something considerably more direct happened while the spacecraft watched. Starting in January of 2019, the asteroid began throwing material off its own surface. The 3 largest events came in quick succession early that year. They occurred on the 6th of January, the 19th of January, and the 11th of February. Particles measuring centimetres across were launched at speeds reaching about 3 meters per second. For scale, the escape velocity at Bennu's surface is only around 20 centimeters per second. Hold both of those figures together, because the comparison matters. Most of that ejected material was moving fast enough to leave the asteroid permanently. Roughly 70% of it fell back anyway, but the departure itself is the point. Nobody has settled which mechanism is responsible for those ejection events. The candidate list includes small meteoroid impacts striking the surface at high speed. It also includes thermal cracking, as the surface heats and cools violently through each rotation. Trapped water vapour escaping from beneath the surface remains a serious possibility as well. It may well be all 3 mechanisms operating at different moments in the rotation. Here is why that matters for the story we are following. Bennu is a potentially hazardous asteroid and one of the most studied bodies in the solar system. We sent a spacecraft, orbited it for over 2 years, and mapped it centimetre by centimetre. We brought a physical piece of it home to laboratories on Earth, and it was quietly throwing material into space the entire time we watched. Nobody had predicted that behaviour, and nobody has fully explained it since. So ask the obvious question about what we would have known from a distance. Without a spacecraft parked alongside, would anyone on Earth have detected those ejections? A few 100-centimetre scale particles produce absolutely nothing that a telescope could register. No coma would appear, no tail would form, and no survey would ever flag it. There is a laboratory dimension to this that deserves mention as well. The return samples from both missions are still being analysed years later. Each new analysis has tended to find more volatile content rather than less. The picture that emerges is not a clean division between rocks and dirty snowballs. It is a continuum, with genuinely inert bodies at one end of the range. At the other end sit classical comets fountaining gas and fine dust across the sky. Between those extremes lies a broad and heavily populated middle ground. Those objects contain volatiles, lose material intermittently, and get nudged by processes invisible from here. We have been sorting them into one bin or the other using a camera. That is the context our missing rock arrived into during the summer of 2026. It was never a bolt from a clear sky, and the warnings were decades old. Understanding why it moved so far, though, requires understanding exactly how a rock breathes. Part 7. What happens when a rock starts breathing? A comet nucleus is not a snowball in the way you would build one outdoors. It is a loosely bound aggregate of rock, dust, organic compounds, and frozen volatiles. Water ice dominates that mixture, alongside carbon dioxide, carbon monoxide, and more exotic frozen gases. Out in the cold parts of the solar system, none of that material does anything. The body sits inert, structurally stable, and completely invisible to any survey looking for activity. Then the orbit carries it inward toward the sun, and the chemistry wakes up. In vacuum, ice does not melt into water and then boil away as steam. There is no atmospheric pressure available to hold a liquid phase together at all. The ice converts straight from solid into gas in a process called sublimation. For water ice, that process becomes significant somewhere around 3 times the Earth-Sun distance. It then accelerates sharply as the object continues falling toward the inner solar system. Our object reaches about 0.79 astronomical units at its closest solar approach. That distance places it well inside Earth's own orbit around the Sun. It receives more sunlight than our planet does, and considerably more than any main belt asteroid. Water ice at that distance is not gently evaporating, it is running hard. Now here is where the thrust actually comes from, and it is worth feeling rather than accepting. A water molecule leaving that surface departs at several hundred meters per second. It does not drift away lazily, it is ejected with real velocity. Let that mechanism settle before we go further, because everything depends on it. Gas leaving in one direction means the body moves in the other. That single exchange is the entire physical basis of this story. Every molecule that leaves carries momentum away from the body it left. The body therefore receives an equal and opposite kick in the other direction. That is not an approximation or a convenient simplification of the situation. It is Newton's third law operating precisely the way it operates inside a rocket engine. The only differences are the heat source and the absence of any nozzle. Sunlight replaces combustion, and the gas escapes in whatever direction the surface happens to face. One single molecule leaving that surface is obviously nothing at all. The measured production rate here was around 1.2 times 10 to the 24th. That figure counts individual water molecules escaping every single second. That output continues day after day around perihelion, orbit after orbit, for as long as ice remains. Now recall that finger pressing against the stalled car on the frictionless road. This is that same push, delivered continuously across decades, with nothing to oppose it. There are 3 features of this thrust that make it far harder to model than gravity. Each one of them compounds the difficulty created by the others. The first feature is that the push is not constant over time. Output depends on how much sunlight reaches the icy patches on that surface. That in turn depends on distance from the sun, which changes continuously through the orbit. Near perihelion, the engine runs at full throttle for a period of weeks. Out near the far end of the orbit, the engine switches off entirely. So this is not a steady shove, it is a pulse delivered once per circuit. That pulse lands when the object is moving fastest and is most sensitive to disturbance. The second feature is that the venting is not evenly distributed across the body. Comet nuclei are not uniformly icy, and they develop insulating crusts over time. Volatiles near the surface deplete, leaving behind a lag deposit of dust and refractory material. That deposit insulates whatever remains underneath, shutting down activity across most of the surface. Escape then concentrates in whichever spots still have access to buried ice. The gas leaves from a handful of specific regions rather than uniformly in all directions. The third feature turns an awkward modelling problem into something close to impossible. The object is rotating while all of this is happening. If venting comes from a few discrete regions, the thrust direction sweeps around as the body turns. Some of that cancels out neatly over a full rotation. Not all of it does, and what survives the averaging depends on several unknowns. It depends on where those active regions sit relative to the rotation axis. It depends on how the spin axis is oriented with respect to the sun. It depends on the thermal lag between peak illumination and peak gas production. So predicting this object's future position properly would require knowing its shape and spin axis. It would require its rotation period, the location of every active region, and their composition. It would require knowing how all of that evolves as the body sheds mass. We know almost none of those things for this particular object. Its rotation period had never even been measured before the recovery campaign began. Radar places an upper bound near 5.4 hours for that rotation. An upper bound, however, is not the same thing as a value. It is worth stating what would be required to do better than that. You would need a spacecraft alongside the object for at least one full orbit. It would map the surface, locate the active regions, and measure the spin precisely. That has been done for exactly 2 asteroids in the history of spaceflight. Neither of them was a comet, and neither was chosen for this reason. So the team did what everyone in the field does under those circumstances. They took the total effect, averaged it, and fitted it as a single number. I want to be precise about what that number actually represents. It is not a physical description of the engine driving that body. It is a summary statistic and nothing more than that. It answers exactly one specific question about the observations already collected. If all this messy behaviour were one smooth push in one direction, how large would it be? That approach works well for describing data you already have in hand. It works considerably less well for predicting data you have not collected yet. The moment the object's activity changes, and it certainly will, the number changes with it. Comets are notorious for exactly this kind of behaviour over time. They produce sudden outbursts, they fragment, and they shut down without warning. Active regions exhaust their buried ice and then go quiet permanently. New regions open when a crust cracks or a fragment breaks away and exposes fresh material. Every one of those events rewrites the thrust term from scratch. One further comparison makes the modelling difficulty feel genuinely concrete. Predicting this object is like forecasting where a balloon will land after release. The air escaping from the neck drives it, and nobody can predict the path. The difference is that a balloon lands within seconds, and this takes decades. So the honest position on this object is narrower than the headlines suggested. We now know it is being pushed, and we know roughly how hard across 2 orbits. We do not know how hard it will be pushed on the next one. We also have no physical model that would let us derive that from first principles. That distinction matters enormously for everything that follows in this story, but it only becomes alarming once you meet the other invisible force acting on these bodies. Part 8. 3 grapes and the force we thought we had solved. In 1899, a Polish civil engineer named Ivan Yarkowski published a short pamphlet. In it, he pointed out something nobody in astronomy had bothered to consider. A rotating body in sunlight does not merely absorb heat from that sunlight. It also re-radiates that heat back out into space afterward, and because surfaces take time to warm and cool, the timing does not line up. The hottest part of a rotating body is not the point facing the sun directly. It is the region that has been in sunlight a while and has had time to heat. On Earth, this is exactly why mid-afternoon feels warmer than noon does. Hold that afternoon comparison, because it does the explanatory work here. The warmest hour of your day is not the hour of strongest sunlight. Heat arrives, accumulates, and departs on a delay, and that delay is everything. Now, thermal radiation carries momentum away, just as reflected light does, so the warm afternoon side of a spinning asteroid radiates slightly more momentum away. The cold morning side radiates noticeably less, and the two do not balance. That imbalance produces a small net force acting on the whole body. The force is tiny, and it is also completely permanent. It acts in a consistent direction determined by which way the object spins. For a body rotating in the same sense as its orbital motion, the effect pushes it outward. Reverse the spin direction, and the same effect slowly drags the object inward instead. The direction of that thrust depends on something wonderfully simple. It depends on which way the object happens to be spinning. 2 identical rocks in identical orbits will drift oppositely if they spin oppositely. For 80 years that idea remained a curiosity that almost nobody could actually use. Then, in 2003, radar measurements of a half-kilometre asteroid detected it directly. That object is called Galevka, and its orbit had drifted about 15 kilometres over 12 years. Gravity could not account for that drift by any arrangement of the planets. Yarkowski's thermal argument predicted it almost exactly, nearly a century after he wrote it down. That Galevka result deserves real recognition for what it actually demanded. Astronomers had to track a half-kilometre rock across 12 years of orbits. They then had to detect a 15-kilometre discrepancy in its position. 15 kilometres sounds substantial until you weigh it against the orbit involved. That path stretches for hundreds of millions of kilometres around the Sun. Since then, the effect has been measured on roughly 500 near-Earth asteroids. It is not exotic physics, and it is not controversial in any way. Any serious orbit determination for a well-observed object now includes a Yarkowski term. The best measured case anywhere is Bennu, and the reason is straightforward. We sent OSIRIS-RX to fly alongside it for more than 2 years. When you can track a spacecraft's position to within centimetres, everything changes. That spacecraft was orbiting an asteroid, which pins down the asteroid's motion extraordinarily well. No telescope on Earth can approach that level of precision from a distance. The result was striking in its precision and its size. Bennu's orbit is shrinking by about 285 metres every year. Steve Chesley, a scientist at the Jet Propulsion Laboratory who worked on that measurement, offered a comparison. He described the force as roughly equivalent to the weight of 3 grapes pressing constantly. 3 grapes applied continuously to a body with a mass near 70 million tons. I need you to hold that comparison, because it becomes the yardstick for everything after. That tiny force is not a footnote inside Bennu's risk assessment. It is the single dominant source of uncertainty in that assessment. That measurement is worth appreciating simply for its sheer precision. 285 meters per year on an object orbiting the Sun. The orbit itself is hundreds of millions of kilometres around. Detecting a drift that small against a path that large is remarkable work. It was only possible because a spacecraft sat alongside the asteroid for years. Bennu carries a small chance of striking Earth in the 2200s. The width of that probability distribution is set almost entirely by surface thermal properties. It is not set by gravity, because gravity we have thoroughly nailed down. It is set by sunlight, heat, and the timing of their release. Now compare those two figures directly, and the reason for alarm becomes obvious. The maximum possible Yarkovsky push here was 1.3 times 10 to the negative 12th. The measured push was 1.4 times 10 to the negative 11th. If Yarkovsky is 3 grapes, then the force acting here weighs roughly 30. I should mention the companion effect while we are inside this physics. The same thermal emission acting on an irregular body does more than push it along. It also applies a torque, which slowly changes how fast the object spins. That process is called the Yorp effect, and over long timescales it matters enormously. Spin a rubble pile up far enough, and it will shed material or come apart entirely. That is one proposed route for creating small icy bodies in the inner solar system. A larger object spins up, fractures, and the fragments expose interior material never touched by sunlight. It is worth dwelling on how long that idea sat unused after publication. Yarkovsky died in 1902, 3 years after his pamphlet appeared. His work survived largely because one Estonian astronomer remembered reading it decades later. For most of the 20th century, nobody could measure an effect that small. The instrument simply did not exist, and the idea remained a theoretical curiosity. It took radar and a century of patience to turn it into a measurement. That history is worth remembering when considering what else we currently cannot measure. So assemble the whole picture and notice its uncomfortable shape. We have known for over a century that small non-gravitational forces act on these objects. We have spent decades measuring one of them with real care and building our uncertainties around it. What the new result demonstrates is that a second force exists in at least some cases. That second force runs an order of magnitude stronger than the one we account for. We did not measure it because we did not know to look for it. And we did not know to look because the object did not appear to warrant it. That is the anomaly, stated as plainly as the evidence allows. It is still not the danger, and the distinction between those two is where this story turns. Part 9. How a whisper turns into a mile. Most people carry an intuition about errors that works fine in ordinary life. A small mistake in your model produces a small mistake in your answer. Wait twice as long, and the mistake grows roughly twice as large. That intuition describes a constant velocity offset well enough for most purposes. It does not describe what happens here, and the difference is the whole problem. What we are dealing with here is not an error in velocity. It is an error in acceleration. An acceleration does not accumulate in a straight line. Instead, it accumulates with the square of the elapsed time. Let me make that concrete rather than leaving it as an equation. Suppose an unmodelled acceleration acts along the direction of travel for 1 unit of time. Call the resulting position error 1, whatever the actual units happen to be. After 2 units of time, the error is not 2, it is 4. After 10 units of time, the error is not 10, it is 100. After 100 units of time, the error has reached 10,000. That is the shape of the curve, and its shape is what makes it dangerous. It begins as nothing, and it stays as nothing for a very long stretch. Then it stops being nothing, and the transition feels abrupt from the outside. For the first year or two after fitting an orbit, that error hides beneath your measurement noise. The object appears roughly where you expected it to appear each time. Everything looks fine, so the orbit gets marked as well determined and filed away. Then the object leaves observing range for 2 complete circuits of the Sun. In this case, that gap ran from 2016 to 2025. Nobody on Earth was checking anything during those 9 long years. Mark that 9-year interval, because it is the actual villain here. Not the ice, not the venting, and not any failure of instrumentation. The gap in observation is what allowed a small force to become a large error. The error compounded silently the entire time, growing with the square of every passing month. When the object finally returned, the accumulated discrepancy stood at 153 arc seconds. There is one more feature of that curve worth stating plainly. The growth does not require the force to increase at any point. A perfectly steady, unchanging push produces this accelerating divergence all by itself. Nothing about the object needs to change for the error to explode. Time alone is sufficient, and time is the one thing always available. Compare that with how measurement errors usually behave in science. Random errors tend to cancel each other out as observations accumulate. Take more measurements, and the noise averages away toward nothing. A systematic force does the opposite of that in every respect. More time does not average it out, it simply gives it longer to work. There is a second effect layered on top of that one, and most explanations skip it. Outgassing thrust acts primarily along the direction of travel, which has a specific consequence. Pushing an object along its own orbit does more than shift it forward on the track. It changes the object's orbital energy, which changes the size of the orbit itself. Change the size of an orbit, and you change how long one circuit takes. A change in orbital period is a change that repeats every single lap. Think of a clock that runs half a second fast each day. On day 1, nobody notices anything wrong with the time it shows. By the end of a month, it is 15 seconds ahead of everything else. By the end of a year, it is 3 minutes wrong, and the drift never reverses. Each day's error is added on top of every error that came before it. That is precisely what an altered orbital period does to a tracked object. It arrives slightly early, then earlier still, lap after lap. Because it arrives at the wrong time, it is also in the wrong place. The timing error keeps feeding the position error on every circuit forever. There is a useful way to picture the difference between these two error types. Imagine 2 people walking away from you across an enormous open field. The first walks in a slightly wrong direction at a constant speed. Their distance from the correct path grows steadily and predictably with time. The second person accelerates gently in the wrong direction the entire way. For the first minute you would struggle to tell the two apart at all. By the end of an hour they are nowhere near each other. Our missing rock was the second walker, and nobody watched the field for 9 years. Now consider what all of this means for the reason planetary defense exists. The entire value of our tracking system is early warning, and everything depends on that. The surveys, the follow-up networks, the risk tables, the proposed deflection missions all assume lead time. We expect to identify a threatening object years or decades before any encounter exists because deflection genuinely requires enormous amounts of time to work. Nobody shoves an asteroid aside at the last moment, and no proposed mission tries. You apply a very small nudge extremely early and let it grow into a miss. Look carefully at the structure of that plan and notice something uncomfortable. The strategy depends on exactly the same quadratic growth described a moment ago. we rely on a tiny applied acceleration compounding into a large displacement across decades. That single sentence describes the entire logic of the deflection test we have already flown. Recall the clock running half a second fast every single day. Now imagine that clock is also the thing telling you when to deflect. Every plan built on its readings inherits the same accumulating error. So an unmodelled outgassing thrust is not a nuisance sitting beside our deflection plans. It is a deflection applied by the object to itself over the identical timescale. Its direction is unknown, its magnitude varies, and nobody authorised it. Worse, it has a head start measured in however many decades we have tracked the object. Let me state the consequence honestly, because inflating it would be a disservice. For any object with a dense and recent observation record, this problem is manageable. Watch something continuously, and the discrepancy appears quickly in the residuals. You then fit the extra term, widen your uncertainty slightly, and carry on with the work. That is irritating for the people doing it, and it is not dangerous. The genuine problem lives with the objects that have gaps in their records. Those are the bodies observed for a while, catalogued, assessed, and then left alone. In those cases, the error has enjoyed years of uninterrupted quadratic growth. Nobody was checking, because nothing about the object suggested that checking was necessary, and by construction, those are precisely the objects nobody has any reason to revisit. The risk is highest exactly where our attention is lowest across the entire catalogue. That is not a coincidence or an unlucky arrangement of priorities. It is the same fact stated twice in two different ways, which means the real threat in this story was never the thing we cannot see. Part 10. The rock we already found is the one to worry about. Every asteroid story you have ever encountered shares the same basic architecture. Something is out there in the dark, we cannot see it, and one day it arrives. The fear on offer is a fear of the genuinely unknown object. That fear is not unfounded, and the historical record supports it uncomfortably well. On the 15th of February 2013, an object entered the atmosphere over Russia. That object measured somewhere between 17 and 20 metres across. It arrived at 19.2 kilometres per second on a shallow angle near 18 degrees. It began fragmenting around 45 kilometres up and released its main burst near 30 kilometres. The energy released fell somewhere between 400 and 600 kilotons of high explosive. That is roughly 20 to 30 times the yield of the Hiroshima device. The shockwave reached the city of Chelyabinsk about 2 minutes afterward. Roughly 1,500 people were injured, overwhelmingly by flying glass. The flash had been bright enough that people walked to their windows to look. They were standing at those windows when the blast wave arrived and shattered them. Around 7,200 buildings sustained damage across the region. Nobody was killed, which was a matter of geometry and luck rather than preparation. That object was completely undetected by anyone before it arrived. It was not spotted late, and it was not spotted and dismissed as harmless. There was zero warning, because it approached from the direction of the sun. Here is the detail from that day worth holding on to. Astronomers worldwide were watching a different asteroid that same afternoon. A 45-metre object called 2012 DA14 passed within 27,000 kilometres. Telescopes had been booked, and press releases had been written for it. While everyone watched the tracked object, an untracked one exploded above a city. Go back further for the largest impact of the modern era. On the 30th of June, 1908, something detonated above Siberia. The airburst occurred at an altitude of roughly 5 to 10 kilometres. Energy estimates range from about 10 to 15 megatons, with some analyses running higher. The blast flattened something on the order of 2,000 square kilometres of forest. That accounts for roughly 80 million trees knocked down in a radial pattern. The current mainstream view points to a stony body between 30 and 100 meters. It fragmented in the atmosphere and never reached the ground, which explains the missing crater. The scale of that flattened forest is difficult to picture from the number alone. 2,000 square kilometres is larger than many capital cities and their suburbs combined. Had that object arrived 4 hours later, Earth's rotation would have placed a city underneath. Nobody planned for that outcome, and nobody could have prevented it in 1908. What has changed since then is only that we would now see it coming. That improvement depends entirely on the object behaving the way our models expect. For decades, a leading hypothesis held that the object had been a small comet. That argument rested largely on the fact that no fragments were ever recovered. The comet explanation has now largely lost, and the asteroid explanation has largely won. But the fact that the debate ran for 100 years tells you something. We could not confidently classify the largest impact in modern history. In July of 1994, we finally watched the process happen to someone else. Comet Shoemaker-Levy 9 had been torn into 21 fragments by Jupiter's tides. It returned and struck the planet one piece at a time across 6 days. The fragments arrived travelling at roughly 60 kilometres per second. The largest of them released energy estimated near 6 million megatons. Its impact scar spanned about 12,000 kilometres, which is close to the diameter of Earth. That week ended the era in which impacts were treated as a theoretical concern, and the deep record contained something far larger than any of those events. Roughly 66 million years ago, an object about 10 kilometres across struck Earth. It landed on what is now the Yucatan Peninsula in Mexico. The crater it carved measures about 180 kilometres across. That single impact ended the reign of the non-avian dinosaurs entirely. Research published in 2024 examined ruthenium isotopes in the boundary layer. Those isotopes indicate a carbonaceous asteroid that originally formed beyond Jupiter's orbit. The same work specifically ruled out a comet as the impacting body. Notice what that particular argument was about. One more time. Asteroid or comet, exactly the same question, applied to the largest impact known. One more historical marker belongs beside those, and it is recent. On the 15th of February 2013, 2 events happened on one day. A tracked asteroid passed safely, while an untracked one detonated over a city. That single afternoon contains the entire argument of this story in miniature. Attention was pointed at the object we understood, and the surprise came from elsewhere. I am not going to talk anyone out of that concern, because it is legitimate. But it is not what this particular story is about, and the difference matters enormously. Here is the twist that most of the coverage missed entirely. The object at the centre of this was never an unknown. It was one of the better characterised small bodies in the entire near-Earth catalogue. Discovered in 1998, with 148 astrometric measurements recorded. It had an 18-year observational arc and an infrared size estimate. It had radar constraints, a measured albedo, and a potentially hazardous designation. Somebody had already computed its closest possible approach distance to Earth's orbit. By every metric our field uses to decide whether an object is understood, it was understood, and it turned up 19 standard deviations away from where it belonged. That is the real danger, and it is not the danger the headlines described. The threat is not the comet nobody has found yet in the dark. The threat is the object we already found, already measured, and already cleared. Think of the catalogue as an enormous filing system with an automatic sorting rule. Objects arrive, the rule examines them, and each one goes into a drawer. The drawers are labelled by risk, and almost everything lands in the safe one. That rule has now been demonstrated to be foolable by a specific property. The property is not rare, and the rule has no way of detecting it. We cleared it using an equation that quietly assumed it would never steer itself. Part 11. 14 suspects, and some of them may be our own garbage. Whenever a result like this lands, the same question arrives beside it. Is this one interesting rock, or is it part of something much larger? I am going to give you the case for a pattern first. Then I am going to give you the strongest arguments against that case. Start with the evidence that makes the case for a pattern look strong. This object was not the first one caught accelerating without any visible reason. Astronomers call this small and growing class dark comets, matching everything described so far. A dark comet shows a non-gravitational acceleration too large for thermal effects alone. It shows no detectable coma or tail through any instrument pointed at it. The class was formalized around 2023 by researchers in the United States. Darryl Seligman, now at Michigan State University, has led much of that work. They move like a comet, but they lack the classic coma or tail of one. In December of 2024, a paper added 7 more of them. That roughly doubled the known population to around 14 objects total. Count that number carefully, because its smallness cuts in both directions. 14 objects out of a catalogue containing tens of thousands is not many. Whether that means the phenomenon is rare or merely rarely caught is the open question. That same work found something interesting in how those 14 distribute themselves. Those 14 objects do not form one coherent group at all. They form 2 distinct populations with different sizes and different orbits. One population contains small objects, tens of meters across or less. Those sit on relatively circular orbits close to Earth's own path. Their accelerations include a component perpendicular to their orbital plane, which is genuinely strange. The other population contains larger objects, hundreds of meters across and upward. Those travel on stretched elliptical paths resembling Jupiter family comet orbits. Our missing rock belongs firmly inside that second larger group, 380 meters across, elongated orbit, Tisserand parameter of 2.9. And the significance of the recent result is not that it added a 15th entry. It is that the result closed a loop that had stayed open for years. Until now, every single dark comet was fundamentally an inference. There was an acceleration with no visible cause and a set of competing explanations. Nobody had taken such an inference and predicted that the object must be venting. Nobody had then gone out with large telescopes and photographed the tail. The orbital anomaly was used as a diagnostic, and imaging independently confirmed the diagnosis. Davide Farnocchia, the navigation engineer at the Jet Propulsion Laboratory who led the study, put it directly. He said that detecting these perturbations can be an important diagnostic tool for planetary defense. Track that carefully, because it changes what an orbit fit actually is. A discrepancy can now be treated as evidence about an object's physical nature. In October of 2017, a survey telescope in Hawaii found something unprecedented. It was the first confirmed interstellar object ever seen passing through our solar system. Astronomers named it Oumuamua, and it was small and unusually elongated. As it departed, it accelerated in a way gravity could not explain. No coma or tail was visible to any instrument that looked at it. One camp proposed the object was so low in density that sunlight could push it. Another proposed exotic ices subliming so cleanly that nothing visible ever escaped. A Harvard astronomer proposed that artificial origin deserved serious consideration, generating most of the coverage. What I will say is that the dark comet framework offers a mundane explanation. The recent result strengthens that mundane explanation quite considerably indeed. It demonstrates that an object can vent enough material to produce substantial acceleration. It can do that while appearing, to a survey telescope, exactly like a rock. There is a more recent case as well, discovered in July of 2025. It is the third interstellar object, and it passed closest to the Sun that October. It also showed a non-gravitational acceleration afterward, attributed to uneven venting acting like thrusters. That object is a confirmed comet by every available measure. Analysis after its solar pass suggested the material coming off it was changing composition. The interior of that nucleus appears chemically different from its weathered exterior. The venting from a body is not fixed, and it evolves as the body erodes. Now let me give you the case against, because it is stronger than most coverage suggested. The first counter-argument is the simplest, and it comes from the researchers themselves. Many of the larger dark comets may not represent a new class of anything. They may simply be ordinary comets whose activity is too weak to detect. On that reading, there is no new physics and no hidden category. There is only a sensitivity limit, which improves whenever somebody builds a bigger telescope. Our object supports that modest view as much as any exotic one. Once they pointed an 8-meter telescope at it, the tail was plainly there. The second counter-argument is considerably more entertaining and rather more embarrassing. Some of these objects may not be natural bodies at all. Brace yourself slightly for this next example, because it is genuinely absurd. The strongest evidence that our catalogue contains errors is not theoretical at all. It comes from objects that were removed after somebody worked out what they were. In January of 2025, an object was deleted from the Minor Planet Center database. It had been catalogued as an asteroid under a provisional designation. It turned out to be a Tesla Roadster launched into solar orbit in 2018. Now there are preprints proposing that specific dark comets are old spacecraft. One argues that a small dark comet is the Soviet Phobos 1 probe. Another argues that a different one is Venera 2, launched toward Venus in 1965. The physics behind those claims is straightforward and rather difficult to dismiss. A spacecraft has enormous surface area relative to its mass compared with a rock. Solar panels are close to the ideal shape for catching sunlight pressure, so an old probe would show exactly the small out-of-plane acceleration observed. If that is correct, then part of the small dark comet population is our own litter. I want to be clear about where all of this leaves the argument. None of it touches the object at the centre of this story. That body is 380 meters across, with a dust tail imaged by 3 telescopes. The specific case here is solid and is not in dispute. What the spacecraft argument undermines is the population statistics rather than the individual case. If some of the 14 are junk and others are ordinary faint comets, the mystery shrinks. The case for a large hidden population weakens accordingly with it. So here is the honest answer to the question that opened this part. We have one confirmed object that passed every classification test we apply. It was being pushed by a force 10 times stronger than the one we correct for. We have roughly 13 other candidates of varying and disputed quality. We have 2,009 catalogued objects sharing that orbital family. 285 of those carry the potentially hazardous label, and we have no method for determining which of them are hiding an engine. The only available test is watching them long enough for the discrepancy to appear. It is a single data point plus a mechanism suggesting there should be more, which is arguably the most dangerous kind of result a field can produce. Here is the detail that almost all of the coverage skipped entirely. Nobody has claimed that a hidden population exists, and the researchers have been careful. The claim is narrower and harder to dismiss than a dramatic headline would suggest. One object passed every test we have, and it was wrong the whole time. It is precisely the kind that gets filed away until the second case appears, and the timing of that uncertainty could hardly be worse, because of what happens next. Part 12. The machine that is about to bury us in new rocks. Two independent things are happening in planetary defense right now. They are moving toward each other, and the collision point is what matters. Here is the first of those two converging developments in detail. Our ability to find new objects is undergoing the largest step change in the field's history. For most of the past 30 years, discovery has been the work of a handful of telescopes. Those were mostly modest instruments, grinding through the sky night after night. The catalogue built up steadily, rather than dramatically over that period. Today there are roughly 38 to 39,000 known near-Earth objects. More than 11,000 of those measure larger than 140 meters. That size class is capable of regional devastation rather than merely local damage. Nearly all the kilometre-scale objects have now been found and catalogued. Those are the ones capable of ending civilization, and that achievement deserves genuine acknowledgement. At the 140-metre level, however, the picture is different. The survey sits somewhere around 43 to 44% complete. The estimated total population at that size is roughly 25,000 objects, which means more than 15,000 objects in that dangerous class have never been seen. The United States Congress directed NASA to catalogue 90% of that population. The deadline for doing so was 2020, and it passed unmet. The mandate was reaffirmed afterward and pushed forward into the current decade. That congressional direction came in 2005 in a piece of legislation. It was named after a representative who championed near-Earth object research. The requirement was reaffirmed again in later legislation during the 2020s. Missing a deadline like that is not evidence of institutional failure. The surveys performed exactly as designed, and the designs were limited by budget. Finding faint dark objects with modest telescopes is genuinely slow work. Now, the step change finally arrives, and its scale is difficult to convey. The Vera-Rubin Observatory released its first images in June of 2025. It began its 10-year survey the following year from a mountain in northern Chile. Weigh that construction figure against what it is expected to deliver. Every asteroid found reduces the size of the unknown population slightly. The cost per discovery falls dramatically once the survey reaches full operation. That facility cost something in the region of $810 million. Its primary mirror measures 8.4 meters across the surface. It carries the largest digital camera ever constructed for astronomical work. But the number that actually matters here is none of those three. It is the sheer width of the field of view it captures. Most large telescopes are narrow by design and by necessity. You point them at a target and take a deep image of a small patch. That is why confirming one faint tail consumed most of a night on an 8-meter instrument. Depth costs you coverage, and that trade-off has governed astronomy for a century. Rubin was designed specifically to break that century-old trade-off. It images an area several times the size of the full moon in every exposure. It moves to a fresh field every few tens of seconds, all night, every night. The result is that it photographs the entire visible southern sky every few nights. Then it does that again, continuously, for 10 years without stopping. That is not a telescope in the traditional sense of the word. It is a change detection machine, built to compare tonight against last week. Its purpose is producing a list of everything that moved or varied. There is a second reason that observatory matters for this particular story. A survey imaging the same sky repeatedly builds an archive of every object automatically. Years later, somebody can return to that archive and stack those images together. An object that appeared as a point in any single frame might reveal a tail. The data for detecting quiet activity gets collected, whether or not anyone is looking. The numbers from commissioning alone should tell you what is coming. Before full operations even began, it found roughly 11,000 previously unknown asteroids. 33 of those were near-Earth objects, and around 380 were distant bodies. 11,000 asteroids during the shakedown period before the real survey started. For comparison, the entire global effort has accumulated 38 to 39,000 near-Earth objects. That total represents about 30 years of dedicated searching by every observatory involved. One object Rubin found deserves mention on its own merits. It is designated 2025 MN45 and measures roughly 700 meters. It completes a full rotation once every 1.9 minutes. Think about what that rotation rate means physically for a body that size. The centrifugal acceleration at its equator is enormous and relentless. A loose rubble pile could not survive those forces and would fly apart. So that object must have genuine internal strength holding it together. It is the fastest rotating asteroid known above 500 meters, and nobody had seen it. That is what a survey of this power actually does. It does not merely add entries to an existing list. It finds the objects that break assumptions, because it examines enough of them. Which is exactly why the timing of the dark comet result is so pointed. Rubin is about to hand us a catalogue several times larger than today's. That catalogue will be dominated by objects with short observation arcs. A survey finding thousands per week cannot follow any single one for long. Orbits will be computed with a model containing gravity and a Yarkovsky term. Each object will receive a risk assessment, and most will be filed as safe. Most of those assessments will be entirely correct, and that should be said plainly. But somewhere in that flood, if our object was not unique, some will have engines. I want to be fair about the other side of this, because Rubin also helps enormously. Finding objects earlier means longer arcs eventually, which tightens every orbit. Repeated coverage means an object that drifts gets redetected rather than lost. For dark comets specifically, a machine imaging the same sky repeatedly is ideal. It accumulates hundreds of exposures of every object automatically, which is exactly what stacking needs. So Rubin is not the problem here, and it may well be the solution. The question is entirely one of sequencing rather than capability. It comes down to whether the tools for auditing the catalogue arrive in time. The alternative is that the catalogue grows too large to audit by hand first, and there is a reason to think auditing it by hand was never realistic anyway. Part 13. What it would actually cost to check every one of them. The obvious response to all of this is that we should simply go and check. Take the 285 hazardous objects in that orbital family. Reobserve them, hunt for discrepancies, and settle the question within a few years. Let me walk through what that would genuinely involve, because the arithmetic is instructive. Detecting an outgassing signature in an orbit requires one of two things. Follow this arithmetic closely, because it explains why nothing has been settled. There are only two ways to catch an object that is quietly venting. Both of them are expensive, and both of them are severely rationed. Either you need a long enough gap for the error to grow measurable. That means waiting years and hoping the object returns somewhere observable from Earth. Or you need measurements precise enough to catch the discrepancy early. In practice that means radar, and radar carries severe limitations of its own. Radar only works when an object passes relatively close to our planet. The return signal strength collapses with distance in a brutal way. The echo scales with the inverse fourth power of the range to the target. Double the distance to an object, and your return signal drops by a factor of 16. Quadruple it, and the signal falls by a factor of 256. So radar is available only in narrow windows around close approaches. For any given object, those windows might open once a decade or once a century. Some objects will never present a workable radar geometry at all. That is why the failed Goldstone attempt mattered so enormously in this story. It was not a routine observation that anyone could repeat next month. It was a rare alignment that happened to be scheduled and happened to fail. The optical route is slower, but applies far more broadly across the catalogue. Here the arithmetic becomes genuinely discouraging rather than merely difficult. Confirming that single tail required the Danish 1.54 metre telescope first. Then it required the Canada-France-Hawaii telescope at 3.6 metres. Then it required roughly an hour and 40 minutes on an 8.2 metre instrument. That last facility is among the largest optical telescopes operating anywhere on Earth. It spent most of a productive night on one object we already strongly suspected. Now multiply that observing campaign by 285 targets. Time on those instruments is among the most contested resources in all of science. Proposals are submitted, reviewed by committees, and ranked against each other ruthlessly. Astronomers routinely wait years to receive a handful of hours. So the idea of simply running this survey is not a matter of deciding to. It would mean displacing a substantial fraction of the world's large telescope time. It would do that for a program returning null results on most targets. And remember what a null result actually means in this specific context. It does not establish that an object is inert or safe. It establishes that the object is not venting brightly enough to see right now. Our missing rock produced 53 null results from a dedicated survey telescope. Those nulls were all correct, and every one of them was also misleading. There is also a human dimension to this that rarely gets mentioned. The number of people qualified to perform this kind of orbital analysis is small. It is measured in the low hundreds worldwide rather than in thousands. Those people are already fully occupied with the objects that appear threatening. Adding a systematic audit of everything else is not a matter of willingness. So the honest position is that no practical auditing method currently exists. The diagnostic technique has been demonstrated, which is a genuine advance. The capacity to apply that technique at catalogue scale simply does not. Consider also what happens to the objects that fail to make the cut. They do not get flagged as unverified or marked with any warning. They simply sit in the catalogue carrying the same confident risk figure as everything else. A database does not distinguish between a number that was checked and one that was assumed. Both appear identical to anyone reading the entry years later. There is one further piece of this that changes the stakes rather than the bookkeeping. If part of the hazardous catalogue is cometary rather than rocky, the labels are not the issue. The consequences of an impact from that fraction would be different. Specifically, they would be considerably worse in two separate ways. Impact energy scales with mass multiplied by the square of the velocity. That squared term dominates every other consideration in the calculation. Asteroids on Earth crossing orbits typically arrive between 15 and 25 kilometres per second. They move in broadly the same direction as we do, in broadly the same plane. The encounter is a fast overtaking rather than a genuine head-on collision. Comets are not constrained by that geometry in the slightest. Bodies arriving from the outer solar system can travel on steeply inclined or reversed orbits. Recall that the fragments of Shoemaker-Levy 9 struck Jupiter at roughly 60 kilometers per second. Because of that squared relationship, arrival speed matters more than anything else. An object arriving 3 times faster delivers roughly 9 times the energy for identical mass. A body you assessed as a regional problem becomes something substantially larger. The second consequence concerns time rather than energy, and it may matter more. Long-period comets are typically discovered on their way inward toward the Sun. Sometimes that discovery comes only months before their closest approach. There is no decades-long catalogue entry for such an object. There is no refined orbit assembled patiently across multiple returns. You find it, and then it arrives, and the interval between those events is short. Every deflection concept we possess depends on applying a small change very early. That includes the one concept we have actually tested in space. The impact experiment shortened a small asteroid's orbital period by 33 minutes. That result was remarkable, and it worked for specific and understandable reasons. The target was a known body in a known configuration with an established orbit. The change had years available in which to accumulate into a real displacement. Compress the available warning time, and that entire approach stops functioning. The technology does not fail, and the engineering remains perfectly sound. The mathematics of small nudges simply requires lead time that no longer exists. So reclassification is not a filing question, whatever the headlines suggested. Whether a hazardous object is rock or ice affects how precisely we can predict it. It affects how much energy an impact would deliver on arrival. It affects how much warning we would have before that arrival happened. All three of those move in the same unhelpful direction at once, and every one of those calculations still assumes we get to look at the object. Part 14. The part of the sky that no telescope can ever search. There is a region of sky that no ground-based telescope can examine. That region is not small, and the reason is embarrassingly simple. Hunting asteroids from the ground means finding faint moving points against a dark background. Darkness is the single essential ingredient in that entire description. You can only search the portion of sky that is currently opposite the sun. Add some region around the edges during twilight, and you have your search area. The part of the sky containing the sun is simply unavailable. The sky there is overwhelmingly bright, and nothing faint survives the glare. That is not a technology problem that a larger mirror can solve. It is a fundamental constraint of observing from a planet with a day side. Any object approaching Earth from roughly the direction of the sun stays invisible. It remains invisible until it is close enough to become dramatic. That is exactly what happened above Chelyabinsk on the 15th of February 2013. 17 to 20 meters of stone arrived carrying 400 to 600 kilotons. Roughly 1,500 people were injured and 7,200 buildings were damaged. Keep that number close, because it is the one that should stay with you. 1,500 injuries came from a rock under 20 meters across. Our missing comet measures 380 meters from end to end. Nothing about that comparison implies any threat, and none exists. It simply establishes what the size classes in this story actually mean. The warning time was 0, and no instrument on Earth could have provided any. Some searching in that direction is genuinely possible during twilight hours. Observers use the brief windows just after sunset and just before sunrise. The sky is darkening or brightening, and the search volume is thin. Those twilight surveys have found real objects, including some that spend most of their time sunward. But the windows are short, the sky is bright, and the coverage remains poor. It is a partial answer to the problem rather than a solution. There is also an atmospheric complication that makes it harder still. Near the horizon you are looking through a much thicker column of air. That air blurs and dims everything, which costs you exactly the sensitivity you need. So, how many objects hide inside that zone at any given moment? The most honest available answer comes from the European Space Agency itself. Richard Moisel, who heads planetary defense there, has stated the position publicly. The number of asteroids hidden in the sun's glare is genuinely unknown. Estimates do exist, and they should be treated as estimates rather than measurements. One analysis cited by NASA suggests a large majority of near-Earth objects are affected. Kelly Fast, who has worked on NASA's planetary defense programs, has framed the shortfall clearly. Of the roughly 25,000 objects at that size, most remain untracked. The choice of parking spot for those telescopes is not arbitrary. The first Sun-Earth Lagrange point sits about 1.5 million kilometers sunward. At that location, the gravity of Earth and the Sun balance in a useful way. A spacecraft there orbits the Sun in step with our planet permanently. It also sits inside Earth's orbit, which changes the geometry of what it can see. From that vantage, it looks outward across the region we cannot search from the ground. That is why both agencies independently selected the same destination for their instruments. Now I want to connect this carefully to everything else, without overstating the link. The sunward blind zone is fundamentally a problem of detection. Unmodelled outgassing thrust is fundamentally a problem of prediction instead. Those are two separate failures with two separate causes and two separate solutions. But they compound in one specific and genuinely uncomfortable way. The blind zone means an object can arrive from a direction we cannot monitor. Unmodelled thrust means an object's approach geometry can shift across decades. Our propagation does not capture that shift, because the force is missing from it. Put those two failures together, and a particular scenario emerges. Follow that scenario one step further, because it is the uncomfortable one. Nothing in it requires bad luck, incompetence, or any missed observation. Every institution performs its role correctly, and the outcome still arrives unannounced. A known, catalogued, cleared object drifts slowly across many orbits. It drifts into an approach geometry that places it in the blind zone. We would not see it coming, and the reason would not be that we missed it. We found it, we cleared it, we stopped watching it, and then it moved. Earlier I said the most dangerous objects are the ones already declared safe. This is the sharpest possible version of that same statement. The fixes for the detection half are known, funded, and under construction. NEO-Surveyor is an infrared space telescope built specifically for this problem. It will operate from a position near the first Sun-Earth Lagrange point. From there it looks outward in infrared, rather than invisible light. That distinction matters considerably more than it might initially sound. Optical surveys find objects by reflected sunlight, so a dark object stays hidden. Infrared surveys find objects by their own emitted heat instead. Darkness provides no camouflage at all against an infrared detector. And these particular bodies, remember, have albedos around 6%. Amy Mainzer, the principal investigator leading that mission, has spent years making this argument. The telescope is currently expected to launch no earlier than September of 2027. The European Space Agency has a complementary concept called NEOMER. It is also an infrared telescope intended for that same gravitational parking spot. It is designed specifically to catch objects approaching from the sunward direction. Current expectations place its launch no earlier than 2030. There is a scheduling reality worth naming alongside those launch dates. Space telescopes slip, and they slip in one direction rather than both. Every major observatory of the past 20 years launched later than first announced. Both of those are real programs with real budgets and real hardware. Neither of them is flying today, and neither will fly next year. There is a grim symmetry in where these two instruments will sit. Both will occupy the region between us and the Sun. Both will spend their operational lives looking back toward the volume we cannot search. So for the immediate future, the blind zone stays exactly as blind as before. There is one encouraging thing to say about the whole situation. When our system is actually watching something, it performs extraordinarily well. And there is a recent case that demonstrates precisely how well it can perform. Part 15. The rock we caught, and why that should worry you more. In late December of 2024, a survey telescope in Chile found something. The object received the designation 2024 YR4. Initial observations suggested a body somewhere in the 50 to 60 meter range. Over the following weeks, more observations arrived and the orbit was refined. The calculated probability of an Earth impact went up rather than down. By February of 2025, it had reached about 3.1%. That number does not sound alarming to most people who hear it. Let me translate it into something with genuine emotional weight attached. 3.1% is roughly 1 chance in 32. Imagine boarding a plane after being told it carried a 1 in 32 chance of crashing. Nobody would board that plane, and no airline would be permitted to fly it. That object was rated 3 on the Torino scale used for impact hazard. That scale runs from 0 to 10, and 3 indicates a close encounter meriting attention. It is the highest sustained rating any object of that size has ever received. Then the system did precisely what it was designed to do. Telescopes right across the world were redirected toward that single target. The International Asteroid Warning Network coordinated observations across multiple continents. That organisation exists specifically to coordinate moments exactly like this one. The observation arc lengthened steadily as more data accumulated each week. The orbit tightened, the uncertainty region shrank, and the impact probability collapsed to 0. The probability was not merely reduced to some comfortable level, it was eliminated entirely, and understanding the reason matters here. The probability was never a measure of how likely the object was to hit us. It measured how much of our uncertainty region happened to contain Earth. More data produced a smaller region, and Earth eventually fell outside it. But the story did not end at that point, and this is the part worth keeping. The risk had migrated somewhere else rather than simply disappearing. Earth was ruled out, and the Moon was not ruled out with it. The probability of a lunar impact climbed to about 4.3% by May. Then the object receded and grew too faint for any ground-based telescope. The final ground observation came in March of 2025. It would not be observable again from the ground for several years. So the team turned to the James Webb Space Telescope instead. Observations were taken on the 18th and 26th of February, 2026. The object was so faint that it became the most difficult such detection ever attempted. Andy Rivkin, an astronomer at the Johns Hopkins Applied Physics Laboratory, led that observing effort. Those measurements extended the observational arc by a further 8 months. They reduced the uncertainty in the 2032 encounter by a factor exceeding 30. On the 5th of March 2026, NASA announced the lunar impact was ruled out. The object will pass roughly 22,900 kilometres from the Moon's centre. The uncertainty on that figure is about 800 kilometres either way. That is a complete and successful planetary defence response from beginning to end. Detection, escalation, coordinated follow-up, orbital refinement, and clean resolution. Every stage of it worked exactly as the designers intended. The Torino scale deserves a moment of explanation because it is deliberately blunt. It was designed to communicate hazard to the public without requiring technical training. 0 means no hazard worth discussing, and 10 means a certain global catastrophe. Most objects that ever receive a rating sit at 1 and then drop to 0. That drop happens because more observations almost always shrink the uncertainty region. Reaching 3 and staying there for weeks is genuinely rare. The warning network coordinating that response has member observatories on several continents. It exists so that a discovery in Chile can be followed up from Hawaii. There is also a separate advisory group whose role is planning actual deflection missions. Neither body has authority to order anything, and both operate by cooperation. That arrangement has worked so far, and it has never been tested by a real threat. Now hold that success directly alongside our missing rock, and notice the difference. The 2024 object was watched continuously by everyone with a telescope. That attention ran from the moment it became interesting until the moment it resolved. Under those conditions, The system is genuinely extraordinary at its job. Errors appear fast when people are looking, and anomalies get chased immediately. Had that object been outgassing, the discrepancy would have surfaced within weeks. It would have been absorbed into the fit, and the answer would still be right. Our missing rock was not being watched by anyone at all. It was catalogued, assessed as understood, and left alone for 9 years. Same institutions produced both outcomes, using the same physics, and often the same people. The results diverged completely, and only one variable separated them. Somebody was looking in one case, and nobody was looking in the other. One further detail from that whole episode deserves close attention. The observations that resolved it were taken by a telescope not designed for asteroids. Webb was built to study distant galaxies and the atmospheres of exoplanets. It happened to be the only instrument capable of seeing an object that faint. Planetary Defense borrowed it, and that borrowing is not something anyone can count on. So the reassurance here is real, and I want it stated without hedging. The system genuinely works when it is given the chance. When we watch an object, we get the right answer. Which is exactly what makes the remaining question so uncomfortable to sit with. Our capacity for watching is finite, and it is about to be stretched enormously. Rubin will deliver tens of thousands of new objects into the catalogue. Almost none of them can receive the treatment that saved us from a false alarm. Scale that problem forward by a factor of several, and the difficulty becomes obvious. Every object added to the catalogue competes for the same finite observing time. The competition is decided by which objects appear to matter most. The triage decision about which objects deserve watching is made by a risk calculation. That risk calculation is the exact thing our missing rock proved can be fooled. And that triage rule is about to face the largest test in its history. Part 16. The 4 years that will settle this argument. Let me separate what we will actually learn from what we are currently guessing. The nearest test arrives in November of 2026. The European Space Agency's Hera spacecraft reaches the Didymos system that month. Didymos is the binary asteroid where NASA deliberately crashed a spacecraft. That impact happened in September of 2022. The target was the smaller body, and the impact speed was 6.1 kilometres per second. The purpose was determining whether we could measurably change an asteroid's orbit. We could, and the measurement was cleaner than anyone expected. The orbital period of the smaller body around its parent shortened by 33 minutes. The uncertainty on that measurement was about 1 minute either way. That is an enormous change, and far more than the impact alone should have produced. The reason connects directly to everything discussed in this briefing. When the spacecraft struck, it threw an enormous plume of material off the surface. That ejector carried away more momentum than the spacecraft itself had delivered. The effect was genuinely multiplied rather than merely transferred across. The multiplication factor is called beta, and the best estimate landed near 3.6. The plausible range, however, runs from roughly 2 to nearly 5. That spread exists because the calculation depends on the target's mass, and we do not know the target's mass with any real precision. That is exactly what Hera is going to measure when it arrives. Pinning down that mass pins down the multiplier at the same time. That converts a successful demonstration into a properly calibrated tool. Notice the shape of that problem, because it should feel familiar by now. We applied a force to an object and measured how much its orbit changed. We cannot convert one into the other, because the physical properties are unknown. That is the identical problem to our missing rock, approached from the opposite direction. There, an object applied a force to itself, and we measured the resulting change. We cannot build a physical model, because we do not know the object well enough. It is the same gap, the same cause, and the opposite sign. The second test comes with NEO Surveyor, launching no earlier than September of 2027. If dark low reflectivity objects are common, an infrared survey will say so quickly. We should know within the first year of operations either way. The third test is the one I find most scientifically satisfying. The Japanese Hayabusa 2 spacecraft, having already returned samples from Ryugu, continues on an extended mission. Its destination is a very small object, catalogued as 1998 KY26. Arrival at that target is currently scheduled for 2031. That particular object already sits on the dark comet list. It belongs to the small near-circular population rather than the larger group. It is also one of the objects where refined radiation modelling might explain everything. So in 2031, a spacecraft will approach a dark comet directly. Either there is ice venting from that body, or there is not. Either way, it settles a question no amount of remote observation can. Take this next date seriously, because it is the one people will remember. Everything discussed so far has been measured from a great distance. What comes next will be visible from a back garden without any equipment. The fourth date is the 13th of April, 2029. An object called Apophis passes extremely close to Earth on that date. It measures roughly 335 to 375 meters. It will come within about 31,600 kilometers of Earth's surface. That places it inside the orbits of our geostationary communication satellites. It will be visible to the naked eye from Europe, Africa, and parts of Asia. It is the closest approach by an object that size that we have ever anticipated. Statistically, an event like that happens perhaps once in several thousand years. Impact has been ruled out for at least the next century. But here is the detail belonging in this particular story. Long-term prediction for Apophis becomes difficult specifically after 2029. A pass at that distance scrambles the trajectory through Earth's own gravity. What happens afterward depends sensitively on non-gravitational forces acting on the body. For Apophis specifically, those forces are currently very poorly constrained. NASA has redirected the OSIRIS-RX spacecraft, now renamed OSIRIS-APEX, to study it. The European Space Agency has a mission concept called Ramses, intended to arrive earlier. The scientific case for both missions is the case running through this entire briefing. We need to measure non-gravitational forces on individual objects directly. Inferring them reliably from a great distance has now been shown to fail. It is worth naming what that Apophis encounter will actually provide. For the first time, we will watch a large object pass through Earth's gravity field. Tidal forces will stretch and squeeze it as it goes by. Whether its surface shifts, cracks, or releases material is genuinely unknown. 2 spacecraft will be positioned to find out, and the answer arrives quickly. So here are the 2 branching scenarios, presented as honestly as I can manage. In the first scenario, our missing rock is simply an outlier. The dark comet population stays small, and some of it turns out to be spacecraft. Neo-Surveyor finds no large hidden population of quietly active objects. Hayabusa 2 arrives in 2031 and finds an ordinary small rock. In that world, this result is a nice piece of science and a useful technique. It changes essentially nothing about how planetary defense operates day to day. It is worth being explicit about what would distinguish those 2 futures. In the first, the count of confirmed dark comets stays near 14 for years. In the second, that count climbs steadily as new instruments come online. We should have a meaningful answer to that within about 3 years. In the second scenario, the confirmed case is the first of many. The reason we have found only 14 is that finding them requires rare circumstances. It requires a long arc interrupted by a gap, followed by a close approach. It requires a radar attempt, and it requires somebody chasing the discrepancy afterward. In that world, those 14 objects are not the population at all. They are the sampling rate of a search nobody designed on purpose. So which of those two scenarios does the current evidence support? The honest answer is that the evidence supports neither strongly at this stage. Anyone claiming otherwise is running well ahead of what has been measured. But there is one observation that keeps pulling me toward the second scenario. The reason our object stayed invisible was not that it was inactive, it was that the dust grains measured roughly 400 microns across. That is coarse sand rather than smoke, and there is nothing exotic about it. No unusual chemistry is required, and no rare configuration needs to occur. It means the visual test we rely on can fail for entirely ordinary reasons. When the mechanism hiding something is mundane, the hidden thing is rarely rare. Part 17. The empty patch of sky that is still empty. Go back to where this started, on the 26th of August, 2025. A 70-metre dish in the Mojave Desert pointed at a specific patch of sky. It transmitted, it listened through the expected window, and nothing came back. On that night, that was a failed observation and nothing more. It was a wasted slot in a heavily contested schedule. Somebody logged it, filed it, and moved on to the next target. Radar attempts fail several times a year for reasons that are almost always dull. 11 months later, that empty patch of sky became something else entirely. It became the most informative planetary defense measurement anybody made that year. The only reason it did is that somebody treated an absence as data. Nobody ended up finding a threat hiding inside that empty gap. The object carries no impact risk for the foreseeable future, and that figure is 0. There is no rock in this story with our name written on it. What there is instead is a demonstration about one specific assumption. That assumption sat underneath every number our field produces, and almost nobody had written it down. Go back once more to that 153 arc-second gap. Converted into distance, the object stood more than 2,000 kilometres from its prediction. That displacement was built one imperceptible push at a time across 27 years. Nobody could have felt any single one of those pushes. All of them together moved a rock the width of a country. The measurements themselves were never the problem in this case. 148 positions were recorded correctly across 18 years. The size estimate was right, the albedo was right, and the radar signature was right. The orbit fit was performed properly using physics that has landed spacecraft on other worlds. Everything measured was measured well, and what failed sat underneath the measuring. The assumption itself was the thing nobody had ever thought to test. The assumption was simply that a rock is a rock, that these objects are passive, that they fall where gravity sends them, and nowhere else. That the object you catalogued in 1998 follows that same path today. For at least one object in that catalogue, that assumption was wrong for 27 years. We discovered it because an antenna pointed at empty sky, and somebody asked why. There is a particular kind of error that this story illustrates well. It is not the error of missing something, which everyone expects and plans for. It is the error of looking directly at something and drawing the wrong conclusion. The first kind leaves a gap in the record that people know about. The second kind leaves a confident entry that nobody has any reason to revisit. Now think about what happens to a finding like this over the coming months. There will be coverage for perhaps a week, most of it framed as a curiosity. An asteroid turned out to be a comet, which is accurate and entirely misses the point. Then, attention moves elsewhere, because attention reliably always moves elsewhere. The real work of examining what this means for those hazardous objects continues quietly. It continues in a small number of institutions, funded at whatever level it happens to be funded. News cycles run for days, and problems like this one run for decades. That gap between the two is the entire difficulty here, because those objects are not waiting for anyone to pay attention to them. They are on their orbits tonight, exactly as they were last year. If any of them are being pushed the way this one was, that push is accumulating. That push accumulated while you were reading this very sentence. It will accumulate tomorrow, and the day after, growing with the square of every passing year. It does that whether or not a single telescope is pointed anywhere near it. There is nothing here to be frightened of on any timescale that should change your week. No date is circled, no object is inbound, and no agency is preparing anything. But there is something worth carrying away about how confidence actually works. Every catalogue is a snapshot of what we believed when we stopped looking. 2009 known objects share that orbital family with our missing rock. 285 of them carry the potentially hazardous designation. One of them has now been confirmed to be pushing itself through space, and the only reason it stayed hidden for 27 years is almost absurdly simple. Its dust grains were slightly too large to catch the light properly. None of that requires anyone to act differently tomorrow morning. It requires only that the assumption gets written down and treated as an assumption. Assumptions that stay unwritten are the ones that never get tested. So the question that opened all of this is still sitting there unanswered. Was that object the rare exception, or the first one we happened to catch? Nobody on Earth can answer that yet, and the honest people say so plainly. The instruments that could answer it are being built right now in Chile and California. One of them begins its full survey imminently, and another launches in 2027. A spacecraft reaches a second dark comet in 2031 and looks at it directly. Until those arrive, the catalogue stays exactly as it is tonight. Tens of thousands of entries, each with a number beside it describing risk. Every one of those numbers computed with an equation that assumes nothing is steering. That filing system keeps sorting, and the drawers keep filling, night after night. Every entry carries a number, and every number carries an assumption underneath it. Somewhere out there a dish will point at another empty patch of sky. The interesting part will be whether anybody bothers to ask why,